In this section, we're going to look at independent samples for two population means. So we're still doing a hypothesis test, but this time we are looking at a hypothesis test to look for a difference between two population means. And the key difference between this section and the previous section is that now we have independent samples. So instead of the matched pairs that we had previously, where we typically had like a pre-test and a post-test or a before and after, and we were taking data on the same variable for the same individual twice. This time we have independent samples, so these are two different populations, each with different individuals or objects in them, and then we're comparing the means for those two populations. Okay, and so if we get going here with kind of the basic setup, we have hypothesis test for two population means when sigma is known for both populations, and hopefully it should be expected that that will end up being a z-test statistic since sigma is known. And then we're also going to look at a hypothesis test for two population means when sigma is unknown, and when sigma is unknown, we're going to use the sample standard deviation of each population for our estimates, and we're going to have a t-test statistic. Okay, so whether we're doing a z-test or a t-test, the basic structure is the same, which is we're going to have two different populations, each with its own mean and its own standard deviation. So population 1 will say has mean mu sub 1 and standard deviation sigma sub 1, and population 2 has mean mu sub 2 with standard deviation sigma sub 2. We are then going to sample from each of the populations. We'll call those sample sizes N1 and N2, which you'll notice are not necessarily the same size. We will then calculate sample statistics for each population. So we'll have a sample mean, a sample standard deviation, and a sample size for each population. And then we're ready to perform our hypothesis test. So first thing I'm going to give you here is the structure of the null hypothesis. So remember, the null hypothesis always tests for no change or no difference. So in this case, testing for no difference would mean that the mean for population 1 was the same as the mean for population 2. And then as usual, we have our standard 3 alternatives. So one choice for the alternative would be that mu1 differs from mu2. That's our two-tailed test. Another choice would be that mu1 is less than mu2. That's our left-tailed test. And then the last choice would be that mu1 is greater than mu2. And that would be our right-tailed test. Okay, so I'm going to next go ahead and give us the test statistics, both for the z-test and the t-test. So just as a reminder here, it says if you know the population standard deviations for each population, you're going to use a two-sample z-test. If you do not know the population standard deviations for each of the two populations, you're going to estimate those with S and use a t-test. Okay. So this one is the more common case because usually we don't know those population standard deviations, but I'm going to give you both test statistics below. Okay, so we're going to start with the t-test. This is, remember, when sigma is unknown for both populations, right? And so in that case, the test statistic T is going to be found by taking the difference between the sample mean for the first population and the sample mean for the second population, and then dividing by the square root of the sample standard deviation squared for the first population over the sample size of the first population, plus the sample standard deviation squared for the second population over the second sample size. Okay, so that doesn't look too bad. And the more complicated part, or I guess the more time-consuming part, is to calculate the degrees of freedom. So if you remember, in a one sample t-test, the degrees of freedom was just n minus 1, just the sample size minus 1. But here for a two sample t-test, the degrees of freedom formula gets a little more complex. Typically, I'm going to show you these formulas, but we're going to do our example using the calculator, and the calculator is going to find all of this for us. So if you wanted to do this by hand, the degrees of freedom looks like this. Okay, so that's your numerator. And then the denominator is going to be 1 over n1 minus 1 times s sub 1 squared over n1, and that whole quantity is squared, plus 1 over n2 minus 1 times s sub 2 squared over n2, and that's squared as well. Okay, so as you can see, that's a pretty messy degrees of freedom calculation. We're going to do it on the calculator and let it calculate that for us. Okay, if we happen to know the two population standard deviations, we would use a z-test instead. Okay, and for a z-test, our test statistic would look like this. So we're still taking, for our numerator, the difference between the two sample means. And then in our denominator, it's going to look very similar to the t-test. We're just going to use sigma instead of s. And again, there's no degrees of freedom with a z-test. That's just the standard normal distribution. And there's only one of those, so we don't need degrees of freedom.